Albert Einstein, born in the city of Kingdom of Watersburg in the German Empire on 14th March of 1879. This is Albert's house. Not only his house, but his workplace and his religious home. Everything that he's ever done is all belong here. Everything has started here, and everything ended right here. This may seem like an old shabby place, but this is where Einstein did all the magic. All his work, everything was here, right here, in this small shabby room.
This is Satyendranath Bose, and he proposed the Bose Einstein Condensate.
Wait, I think I've got this. I think I know. Quantum statistics. I have to send this. I have to send this to Einstein. He is my close friend. I will go now. I will send this. I have found it. I am successful. This is the man we have been waiting for. Einstein. Everything. Successor, producer, inventor, the master of masters. Einstein. Albert Einstein.
This is better from both.
Well, this is good, but not enough. Considering a collection of non-interacting particles, which can be each be in one of two quantum states, and if the two states are equal in energy, each different configuration is equally likely. I'll have to talk this again to the man who sent this post.
I have to telegraph post. This is very important.
Mr. Einstein, how are you doing, sir?
I'm doing very well.
That's awesome. Let me get your door. Let me get your door.
Yeah.
This is our culture. We have manners, right?
Very good.
By the way, namaste.
Namaste.
Yes, it's our culture. Okay. Anyway, right, I got your telegraph and I knew there was a problem. Such a smart man like you calling me. There must be something, right?
Yes.
So please show me what is
Let's
there.
get to
So,
work.
Mr. Einstein, I've seen that you are thinking there's problems. So what we are going to do now is that you take a rest. I'll work on it. I have some statistics and stuff, you know, the study, the measure work. I have it. So I'll work on it. By the time you take a rest, alright, that'll be good.
Great.
That'll be good.
It's very cool, right?
Alright.
Are we cool?
Alright, sir.
We cool?
Bye bye. Thank you.
Sports is working.
Well, Einstein has done great work here, but I've come to, let's say, a conclusion. My error, is a simple mistake. Similar to arguing that flipping two fair coins will produce two heads 1/3 of the time. That would appear obviously wrong to anyone who has the basic simple understanding of physics, and including statistics actually over here mainly. However, the results it's predicted agree with the experiment, and I realized that it might not be a mistake after all. I took the first time look at the position that the Maxwell and Boltzmann distribution would not be true for microscopic particles, where fluctuation due to Hinsberg uncertainty principle will be significant. Thus, I stressed the probability of finding particles in the phase space. So, I have come to a conclusion that my mistake was a very simple mistake, but now I made it. I'm smart and I'm successful. So, realizing my mistake, I will go to Einstein. I must go to Einstein and tell him, sir, I am sorry. I will work this out and I will give you the final. And now here we are. Conclusion, professional, cool. Mr. Einstein, sir, alright, I hope you had a good sleep. So, what I wanted to tell you was that I have worked it out and the mistake has been resolved. It's a simple small mistake. So, the working has been put onto your table.
So, Mr. Einstein, as you can see my work is completed. I will give you a briefing through it. So, if you can see, the critical temperature is equal to N, which is known as particle density, divided by the Riemann zeta function, and then 3 upon 2 inside the brackets, closing the bracket, and it will be powered by 2 by 3. That's the power. And then 2 pi, which h, the sign that looks like h, is reduced Planck constant square divided by a m, which is mass per boson. And then the k that you see over there with the b, small little b, capital B, but below it is the Boltzmann constant. Alright, Boltzmann constant. That is equal to 3.31, which further gives us the calculation that reduced Planck constant square and n, which you see is particle density, 2 by 3, that's the power, divided by m again that you see is mass per boson, and then the kb is Boltzmann constant. So this is the basic explanation I can give you, sir. Thank you.
Alright, so all I have to tell you was that I'm done, and it's a great pleasure to have been working with you.
Me too. It's
Alright,
great
sir.
pleasure.
Sir, so I would like you to please walk me out. And sir, I was just telling you, you're honorable person. Great job, great, and speechless, sir. Thank you.
Thank you.
Alright, sir.
To conclude, the Bose Einstein Condensate, state of matter of a dilute gas of weakly interacting basins confined in an external potential and cooled to temperatures very nearly absolute zero. Under such conditions, a large fraction of bosons occupy the lowest quantum state of external potential, at which point quantum state of the external potential affects and becomes a very apparent piece on the macroscopic scale. For years we have been depending on these great scientists. They have developed everything we have today: the technology, the skill, the average. Now it's our turn. We have to mend the ways, using their skills, using their time, their effort, and what they left behind for us. The Bose Einstein Condensate.
Thank you for watching.